Hello everyone, I welcome you to the course Unmanned Air Vehicle Design. In today's lecture, we're gonna see about optimum length to diameter ratio of an unmanned air vehicle. The optimum length to diameter ratio is also known as slenderness ratio, which is a crucial parameter determined during the fuselage design process of an unmanned air vehicle. This ratio, along with the fuselage length and maximum diameter, is primarily influenced by a range of design requirements. Design objectives for the optimum length to diameter ratio are: the determination of the optimum length to diameter ratio is driven by several objectives reflecting various engineering and operational consideration. Lowest zero lift drag. This objective is directly related to aircraft performance. The fuselage typically contributes 30 to 50% of the aircraft's total zero lift drag. To achieve low drag, the fuselage cross section should ideally resemble an airfoil shape incorporating streamlining. This includes adding a semicircle to the nose and a cone or a semicone to the rear. For example, imagine this is the section of my fuselage from the top, and it will have either a semicone like this or a semicircle like this, giving a streamlined shape. The top view of the fuselage is recommended to follow a symmetrical airfoil to prevent any yawing movement. If we see from this axis, on the top view, this will be symmetrical. Whatever distance we have from here, the same distance will be on the either side, which will enable its yawing movement is streamlined. Lowest wetted area. This also contributes to enhancing aircraft performance. Lightest fuselage. This objective addresses the weight requirements of the UAV. Maximum internal volume. This is essential for satisfying operational requirements. The fuselage must accommodate various components including payloads, communication system elements, and autopilot compartment. The largest component, example, engine or a satellite communication, often dictates the maximum diameter of the fuselage. For instance, the Global Hawk's distinctive bulge houses a 48-inch wideband satellite communication antenna. Lowest mass moment of inertia. This is vital for meeting controllability requirements, and the greatest contribution to aircraft stability is the objective which ensures UAV meets its stability requirements. The fuselage can generate a significant portion of the total lift, potentially as much as 20%. Although in a basic configuration, it typically provides around 5% of the aircraft's lift. Lowest cost to fabricate is a key consideration for manufacturing cost. Trade-offs and recommendations. Achieving an optimum length to diameter ratio involves complex trade-offs, particularly between cost and performance. A short fuselage tends to have lower weight but may result in higher drag. This configuration is often preferred when minimizing weight is a primary goal. Conversely, a long fuselage generally has a higher weight but can achieve lower drag, making it more desirable for optimizing performance. From a structural standpoint, the most efficient shape for a slender pressurized fuselage is a cylinder with hemispherical end caps. This configuration with a length to diameter ratio of 1 provides the lightest fuselage and lowest wetted area. However, this shape leads to a large frontal area and very high drag, rendering it unsuitable for optimal aircraft performance. For most low-speed unmanned air vehicles, a fuselage slenderness ratio is between 5 and 10 is recommended to achieve low drag. The ultimate solution for lift generation and drag reduction is a blended wing fuselage design, for example X45 and X47, where the wing smoothly integrates into the fuselage, allowing the entire structure to generate lift and minimize drag. Conclusion for this: balancing competing objectives. The optimum fuselage slenderness ratio for a UAV must balance conflicting design goals such as drag reduction, weight minimization, internal volume, and manufacturability, requiring careful trade-offs between aerodynamic efficiency and structural practicality. Recommended design range: for low-speed UAVs, a fuselage length-to-diameter ratio between 5 and 10 is generally ideal, offering a practical compromise between low drag, sufficient internal volume, and manageable structural weight. Advanced optimization techniques, which is used to effectively navigate the complexity of this design trade-offs. Multidisciplinary design optimization methods are essential, enabling integrated decision making across aerodynamics, structures, stability, and cost considerations. These are the references used for the lecture. We'll meet in the next lecture. Thank you.